So this is the third lecture on G inverse. Just briefly recall the concept of G inverse. So what is G inverse? Again, we know the G is a G inverse of, so G inverse, lecture 3. Now G is a G inverse of A. So when there are two equivalent conditions, one is AGA is equal to A, and another condition is these two are equivalent. So 1 and 2 are equivalent. This is not and, this is equivalent. For all or any y belongs to the column space of A, x equal to gy is a solution. Solution of Ax equal to y. So remember, the second condition is more geometrical, more motivational, but the first condition is for checking just the say something is G inverse or not. So check whether this every y belongs to column space of A, there is a solution x equal to gy. That's checking is slightly tough. Rather, AGA is equal to A, that's checking is easy, because here just A is given to you, G is given to you, and just which check whether AGA equal to A or not. But the second condition, which is equivalent condition, A and G is given, but there is no such x and y is given. So we have to prove that for every y there is x. So we need a arbitrary y. So computational purpose or checking verification purpose, one is important, but for theoretical conceptual thing and motivational part for geometry, this the second part is important. So what is actually the second thing is, so we know what is, say Ax equal to y. This is the equation. We know there is a solution if and only if that y is in the column space of A, because we know this if Ax, so here A and this x here, say no, this is nothing but a linear combination of the columns of A. We know, so this is a linear combination of columns of A. So that means your y is actually the linear combination of columns of A. This column y is a linear combination of columns of A. That means y is belongs to the column space. If y is not belongs to the column space, there is no solution. So if there is no solution, okay, if there is no solution, then we can't find any x. But if there is a solution, there is maybe unique x, or there may be infinitely many x. So what is then G? G is nothing but the reverse way. So x equal to then gy. That means now x is a linear combination of then columns of y. So okay, take so column space, like say this is a subspace of column space is a subspace of what? So if it is a n cross n, and this is a m cross 1, this is n cross 1, so it is a column space of A is nothing but a subspace of R or F. If you take any column, any field, it's a complex number or any other field, we usually take the real number. For any field, it is just f to the power n. So number of equations, basically, not the number of variables. So it is number of equations. So column space of A is actually the subspace of the vector space f to the power n or r to the power n, where the underlying field is A for real number. Now we just take a visualization. We take this as a, say, this is my say column space. This is a column space, and this is the whole, say it is R3, say n equal to 3. So it is a whole R3, and your column space is just a subspace which is a plane. We know the subspace of the whole space, three-dimensional space, Euclidean space, just the whole R3, that is a one subspace. The other subspace are the plane passing through origin, that is a two-dimensional subspace, and line passing through the origin, that is a one-dimensional subspace, and that's the singleton origin, the only one zero vector, is a zero-dimensional subspace. Now, this is a column space of A. Now, if we have a vector on this column space, that means the vector lies on this, say, remember that column space, all column of A is actually in between this. So, say these two are, so this one is one vector and this is another vector of A. Then we have several other vector also. Say another vector, that column of A may not be independent. Column of A may be dependent. So if they are dependent, then there are more than two vectors. Say then it is a dependent. That means your number of columns is more than 2. Then all the columns must be dependent, because we are just in figure we take two-dimensional column space of A dimension 2. This is for illustration. Now these red vectors are the column of A, and that generates the whole plane. This is origin. This is origin, null vector. And now this is your y. So this is our y, this vector. And if this vector in this plane, then there is some x. That means there is some x1, x2, xm. Say this are the, say a1, a2, like a3, or maybe there are more than 3 columns, and there are more vectors. So we have to find some x1, x2, xn, such that y, the vector y can be written as x1 a1 plus x2 a2 dot dot xn. Then x1 x2 xn is the solution actually. Now if these are a1 a2 am are independent, then there is a unique solution, and if it's not independent, then this is an infinite many solution. We know that. Now if y is outside that space, if what happens then? If we take the y is outside that, if we take y is outside that, then for this y, that green y, we have no solution. So for this y, no solution, because we can't write that y in terms of the vector a1 a2 an, because a1 a2 an in the plane and this y is outside the plane. The plane means the column space of A. But for this black y, we have this for this y. For this y, solution exists. So this is the basic idea. Now, whatever solution exists or not, the G inverse always exists. The G inverse does not depends on y basically. G inverse actually depends on the column space of A, that column of A. That only the A vector. G depends on the only A vector. G is a function of the A vector, A matrix. It does not depends on y. So before getting y, you can find G, and then you find the solution using that y. So whatever is, y is in G or in y is in the column space or not, that G, that the G inverse of A is always exists. Now what happens if we have, say, y is a vector. So we are taking another diagram. Say this is the column space of A. So consider this is the column, this black plane is the column space of A. Now we are taking a vector y, say, which is outside the column space. Y does not belong to the column space. But we are considering this vector gy. G is the G inverse y. What happened? This is not the solution of y, x equal to y. So in that case, a g y must not equal to y, because there is no solution is there. There is no solution. So there is no such solution of ax equal to y. So that's why if we put replace x by gy, then this is not a solution of ax equal to y. That means a gy not equal to y for if y does not in the column space of. If it is a column space of y, then a gy equal to y. Now the question is, okay, there is no solution, okay, but what is the solution? What is the element of the column space which is if y is actually in the column space of A, then we get gy. Okay, now we replace this. We have another idea, say. So we have one more thing that now consider this is the subspace of Fn. Now consider the solution space. What is the solution space? Now consider the solution space. What about the solution space? Now consider where x lies. Now Ax equal to y. Now consider all solutions. So now solution in Fn, x is m cross 1. X is m cross 1. So now x in Fm. So this is called solution space. Solution space. And this is empty. This is phi set if y does not belong to the column space. Now this is actually the set of all thing gy, because gy is the solution, and gy for where g is any g inverse. G is any g inverse. G inverse of A. So there are several g. Y is fixed. Now we know that Ax equal to y, the solution is gy. So x equal to gy, then gy belongs to Fm. This is a subspace of Fm. Now collect all such gy, that is all such solutions basically, and for every g there is a solution, and the any solution can be written in this form. That's why these two are equal. So if x is a solution, then we can write that x as a gy for some g. That is the equivalent condition. So if g is a g inverse, then this is a solution. If this is a solution, then g is a g inverse of A for some g inverse. This is the very first theorem. Now these two sets are equal. Now we change your g, and if there are only one g inverse is a unique solution. If there are more than one g, is actually it will be infinite. If there is more than one, then it will be infinite. And if there, but it may so happen that there are infinitely many g, but this set is phi. Why? If y is not belongs to the column space of A, then gy, sorry, these two are equal if I take y in the column space of A. Now what happened if y is not in the column space of A? If y not in the column space of A, if y is the column space of A, then gy is the solution of this. And if Ax equal to this can be written as this. But if y is not belong to the column space of A, then the solution space and these two are these are not equal, because this is a phi set. This is phi. But this collection, that gy, g is a g inverse of A. This is not phi. This is not phi. So if y is not in the column space, then this solution space is phi. But this is not empty, because g always exists. For every year there is some g, and you have y. So gy, you can just find gy. So this is not empty. So these two are not equal. Equal if y in the column space. Now just draw this thing. Try to visualize all this thing. So let this is your gy. So this is your say which space? So this is your, this is subspace. This solution space is subspace. This is also a subspace, and okay, that may be your, this is maybe your solution space that are equal. So this is a solution space that may be phi, and now you are taking that in the solution space you are finding some solution gy, and our target is to find such a gy with minimum norm. We want to find the, remember that okay, no, there is a problem. Sorry, this is not a subspace. Oh, sorry, there is a mistake. This is not a subspace. May not be subspace. Actually, it's not subspace. Not a subspace unless y equal to 0. If y equal to 0, then it is subspace. It is a system homogeneous equation. But is it not y not equal to 0, then it is not a subspace. We know ax equal to y. If y not equal to 0, then 0 is not a solution. X equal to y is not equal to 0. It's non-homogeneous equation. In non-homogeneous equation, that y is 0 is not a solution. So, so this, that means your solution space, or the set of solutions, you can't say it is a space, it is a set of solution, is also called affine space. Solution set, it's also called affine space. Now this is not a solution. This is not a subspace of Fn. It's subset but not subspace. Now say origin is outside there, right? So every element here is a solution. Every vector. So from origin to this, is every vector is a solution. This is solution. This is solution. This is gy, right? But we want to find the solution which is minimum norm, which is the least norm. So perpendicular thing. We want to find that solution, and our target is for which value of g we have this black solution, that black vector, which is the minimum norm among all such solutions. Now, obviously, if y equal to 0, then that 0 thing, that the 0 is also solution, 0 is the minimum norm. And in that case, 0 is the minimum norm, and if since y is 0, you can take any g. Oh, in that case, is this equal? If y equal to 0, then ax equal to 0, gy is always 0, right? Oh, you can't say these are equal. Basically, you can't say this. There is a mistake. You can't say these are equal. Basically, why they may not be equal? Because if y equal to 0, in that case, this right hand side set is 0, gy equal to 0, but the set of all solution ax equal to 0 may not be the only 0 solution. So it may be both sides. It may be that solution space may be phi set, still that gy set is not phi. And the other way, it may so happen that if y equal to 0, then that gy collection of all gy is just a singleton 0 set. Singleton 0 set containing single just 0. But the left hand side set, that x such that ax equal to y, that may not be the only 0. There's an infinite many solution. So no question of equality then in any case. So just a correction. And now what happen if y, now consider y as a column space of A, then there is a solution, and there is a collect all this solution, that is called affine space. That is actually this space is affine space is actually this solution space. What is the solution space? You know from the vector space theory that solution space is nothing but some linear shift of some x0 plus that set of all solutions, say S, where x0 is a particular solution of that and S is a collection of all sort of all solution of the homogeneous system, corresponding homogeneous system. If x satisfies that, the x equal to 0 and x0 satisfies this, then x plus x0 satisfies a into x plus x0 equal to y. So it's a linear shift, and that is called affine. If S is a subspace, then some vector, non-zero vector plus A, the subspace is called the affine space. And so this is the solutions thing is the set is the affine space. In 3 dimensions, it may be plane, it may be line, but it's not passing through origin. So all the vectors in that solution set have non-zero norm. We want to find the minimum such vector, which is for which value of G inverse we got this the minimum norm vector. The distance is least from the origin. That is the idea of least square G inverse. So least square G inverse has, again, there is two equivalent condition. The one is more motivational and more geometric, and another is more algebraic. So what is we have this theorem that it's a minimum norm G inverse, number one. This two, number one. This is a minimum norm G inverse. What is the minimum norm G inverse? That is GA transpose is equal to GA. This is algebraically we can easily find that whether GA transpose is symmetric or not. But there is no such motivation. Why take GA transpose equal to GA? So we want to find such a G inverse of A such that GA is symmetric matrix. But this is actually equivalent to say that this is more visualizable, that for any y in the column space, otherwise that is just empty set, there is no such solution. X equal to gy, this is a solution. We know this is a solution because it is a G inverse is a solution of Ax equal to y. So this is solution of Ax equal to y. So because G is a G inverse, that is always true. But the extra condition is there, GA transpose equal to GA, and for this with minimum norm, with minimum norm. What is the idea of minimum norm? So if for some G, if GA transpose equal to GA, then this actually implies that what is the minimum norm is. So take any other G, take other G, another say G dash is any G inverse of A, may not be minimum norm, G inverse of A. Then if you have this we know this D dash y is a solution. Obviously G dash y is a solution of Gx equal to this Ax equal to y, because G dash is G inverse. But that norm of this is greater than or equal to norm of that Gy, a special Gy. The G is with this GA transpose equal to G. The extra condition is there. And this is true for all y in column space of A, not only for a single y, every y column space of A. That G transpose y, the norm of G transpose y is this. So this is the sort of minimum norm. So before proving this, we prove one more lemma. So if A is a m cross n matrix and G is a G inverse of that, G is a G inverse of A, and y belongs to column space, we have to take y belongs to column space, otherwise no solution. Then what happen if then the set of all solutions x then the set of all solutions that x such that ax equal to y, this is set of all solution, is just nothing but the set of solution, then any solution is nothing but the collection of this collection gy plus I minus ga z. Now z is arbitrary for any z. So z, what will be the order of z? Z belongs to what? What will be the order of z? This order of z is what? That A is m cross n, x is your n cross 1, y is m cross 1, g is n cross m, this I is ga is n cross n, and I is n cross n, so z is n cross 1. Z is n cross 1. Z is n cross 1. So Fn. So this two set is equal. Just so you can, if you find just only one single G inverse G, any particular G, fixed that G, then the all solution is not Gi is the solution, Gy is the solution. The other solution is Gy plus this part, I plus minus Ga Z. You can take any Z. So once you have a one solution, you get the all solution. Why this is so? So proof is this. So we have to prove this is a solution. Then we have to prove any solution can be written in this form. So why this is a solution? Since now the proof is like that, so y is belongs to the column space of A. That means what happens? That means your y equal to actually AV, because it's the column space of A. So it's AV for some A. Now for any z, j is any z, so you have to check whether this is solution or not. So you have to put in the equation value the gy plus I minus ga z. Now we have to check whether this is y or not. This is agy plus whatever. This is a minus aga z. Now this is 0. A minus aga is 0, so it is agy, and we know the agy is actually that agy is y is now av, so it is aga v, and aga equal to a, so it is av equal to y. So it's done. So we got this. So this satisfies this solution ax equal to y. So this is solution. Now otherwise you have to conversely have to prove that any solution can be written in the form. So take any solution, y is the any solution, u is the any solution, so au equal to y. Now whether we have to show that u can be written in this form. Now how do you show this? U can be written in the form. So we just put u minus z, put z equal to u minus gy. Put this, and now what about gy plus I minus this, and put that z u minus gy. Then what happens? Gy plus u minus gy minus gau minus plus gagy. gagy. And then gy cancel, u minus gay, ay is y, so au is y, whatever. Is this u? This g by j cancel out, and au equal to y. This is GAU plus GAGY. Is this Z? Now AU equal to Y. We don't know whether G equal to A G or not. So if it is reflexive, then GAG equal to G, but second question is correct. GO minus GAU plus GAGY. Okay, right. It's, you just put here, U minus GY, AU equal to Y, and GAG, you put Y equal to AU, right? Replace that Y equal to AU. Then this AGA is a GAY, right? Right. So this is Y, U. So this is actually your U. So U, we have this U is a solution of AX equal to Y. Then U can be written as GY plus some A minus GA into some arbitrary J. U minus that Z is U minus UI. So we have these two set are equal. So if your U is this of this form, then this is a solution, and if U is a solution, then U can be written in this form. So this is the important theorem, because this actually specified the all these solutions of Ax equal to Y. Once we have a one G inverse Z, Gy is a solution, we know, and the rest, the all solutions is a set of that. So Gy that plus that extra part. Extra part is I minus Ga into Z. Z can be any vector in Fn. So this theorem is important to prove the next thing. The next part is this. That theorem we written in the previous slide, that if A is a M cross N matrix, then A is the minimum norm. That means Ga, not Ag, Ga transpose is equal to Ga. Then this is if and only if this is the minimum norm, that for any Y belongs to column space of A, that X equal to Gy is a solution. This is a solution, obviously, but this solution, because G is a G inverse, is a solution of Ax equal to Y, but that solution, the special solution for the special G with minimum norm is a solution with minimum norm. This is if and only, both sides you have to prove. So what will the proof? So first we prove once, right? This implies thing. So Ga transpose equal to J, then we prove it is a minimum norm. Now we know Ga, Gy. What about the Gy? So G, the norm of Gy. So we have to show what we have to show that norm of Gy less than or equal to that norm of Gy must be less than or equal to that. That idea is this. So we have to prove that this thing is the list. We have to show this is the list thing. So that part, that black is that solution is a list among the all. Is actually that Gy, that the special G, that must be less than or equal to norm of any other solution. But what is the any other solution? Any other solution is like that, Gy plus I minus Gaz. This is any solution. So you have to, for any solution, this norm is big greater than that norm of Gy. You have to show this. So to show this, Now y is in the column space of A, and z is any vector. So what happens? Now that norm of gy minus I minus plus I minus gaz, that norm square, this is equal to, we know this is the inner product between gy plus ig, right? We just so we know norm of A plus B vector square, which is the inner product of A plus B and A plus B. Then this is the inner product of AA, then inner product of AB, then inner product of BA, then inner product of BB. But inner product of AA is norm of A square, inner product of BB is norm of B square, and inner product of AB and inner product of BA is same. Then we have to take the real, we have to take this field as a real. That is a field. Otherwise, if AB equal to BA bar, if it is a complex, then it is a BA bar. So we take as a real field. So it is twice of AB, inner product AB. So here it is just a dot product. So what it will be then? Then this will be gy norm square plus that thing, that one more norm square, I minus ga z, that square, plus twice of the inner product, that means dot product, that will just ag. What is the inner product of two vector? It is x transpose y. So inner product of xy is x transpose y. So it is gy transpose. So gy transpose is g transpose y transpose g transpose, then I minus ga z. Now y belongs to column space away, so y equal to some ay, au for some u, because it is a solution. That is important. Now whatever. Now this part, that y transpose g transpose I minus ga z, what is this? This is u is y is au, so it is y transpose is u transpose a transpose g transpose I minus ga into z. So it is u transpose. Now what is this? This is ag. So we assume that, what do we assume here? We assume that here we assume that ga transpose equal to ga. That means a transpose g transpose is ga. A transpose g transpose is ga. So it is ga. A transpose g transpose, it is ga transpose, which is ga. We assume that it is ga. I minus ga z, and that is u transpose ga minus ga ga z. Now aga is a, we know, so it is 0. So it is null matrix. That means what we get? We get this part is goes to 0. This is, yes, this is 0. So we have this, and that means it is less than or equal. This is greater than or equal to norm is always positive. So this is greater than or equal to mod of gy whole square, norm of this. So that we prove the one side. So this is a basic idea. We have to prove that product term is 0. That is, this idea is used in many situations where this inner product or dot product or some this matrix multiplication involved. We actually prove actually this is the idea of the perpendicularity, orthogonality. So the dot product is 0. That's why this something, it is basically the Pythagoras theorem. Some a plus b whole square equal to a square plus some sort of, it's a perpendicular to a square plus b square in vector. Otherwise there is a dot product term. 2ab cos theta there is, we know, in vector. Now we have to prove the other way, from right to left. Now from right to left, what we have to prove? Since now we have to take the conversely, we have to take that it is a minimum norm. So we assume there is a minimum norm, and then we have to show ga transpose equal to ga. Now y belongs to that column space. So x equal to G is a solution. We know that is a solution. Now G is G inverse of a GA. Now for all Z and for all Z and all U and A, what happened? This is 0 less than or equal to, you know, norm is always positive, greater than or equal to 0. So this square plus that part, this is transpose actually. A minus GA Z. This is for only Z and U. Now you just replace that U by alpha U. So for any alpha scalar, then what happens? Then your U transpose A transpose G transpose I minus GA Z is less than 0. And we choose sufficiently large, alpha, positive alpha. Then what happens? If you choose positive alpha, then it's contradict. It can't be negative. So it is a contradiction. Now similarly, we can take, if U transpose A transpose G transpose I minus GA Z is positive, then choose alpha and choose alpha large and negative. In that case, again contradiction, can't be positive. So what happened? That means this is 0. This part is 0. Product term is 0. We proved that product in the previous part. We proved this in this product term is 0 using GA transpose equal to GA. But here we prove it from the minimum norm that GA transpose GA is because it is a minimum norm. This part cannot be positive, cannot be negative, because this plus something norm is greater than or equal to 0. This proof this is 0. So that means what happens? That means okay, we conclude this, that U transpose A transpose G transpose, that is 0. Then we have to show that only that GA transpose equal to GA. That we have to show. Now this is true for all U and all Z. That means since it is all U and all Z, we can conclude that A transpose G transpose I minus GA is equal to 0. Now then what happened? Then A transpose G transposed, A transpose G transpose minus, this is GA whole transpose into GA equal to 0. So just taking the right side. So this equal to this. A transpose G transpose equal to GA whole transpose. Now, is it proved that this is symmetric? GA is symmetric? Yes, because we know some matrix A transpose is symmetric. We know for any matrix A transpose is symmetric. So that GA transpose J is a symmetric matrix. Is symmetric. We know any matrix for any matrix A transpose A is symmetric. So this is symmetric. That means your A transpose G transpose, which is nothing but GA transpose. So GA transpose is symmetric. And some transpose of a matrix is symmetric. Matrix is symmetric. A transpose symmetric means A transpose equal to A transpose. So A equal to A transpose. And that implies actually GA is symmetric. And that's completely simple. So this is the basic idea of that least square G inverse. Least square G inverse is such a G inverse that GA is a symmetric matrix. In that situation, this is the least among the all solutions. All solution. Assume that solution exists. That is the basic idea of least square G inverse. So sorry, it is called minimum norm G inverse. So it is a minimum norm G inverse, and next one is the least square G inverse. This is a minimum norm G inverse because it is a least among the all solution. Norm is the least. What about the least square G inverse? Least square G inverse is the other way. If AGA transpose equal to GA AG, then we call it's a least square G inverse. And similar idea is this least square G inverse. And similar idea is this, that if it's a least square G inverse, if and only if this two are equivalent for any x and y. Now you can take any xy. Now it may not be that in the solution space. Y may not be in the solution space. Solution may not exist. For any x and y, this norm distance between G, because this is now not the solution. This is the previous thing. This idea. This thing. Now y may not be in the solution. If y in the solution in the column space of A, then we have this idea of minimum norm. We have to find the list such a G such that for which this solution is a minimum norm. But if now consider y may not be in the solution space, in this column space, then there is no such, maybe no such solution is there. In that case, we can find AGY, but AGY is not a y. AGY not equal to y. This AGY may not be equal to y for if y not belong to the column space. Then we actually want to find that such a thing that AGY now AGY and y, the difference must be the minimum among the all such AX minus y. This is the idea. So in that case, if it is AG equal is AG is a symmetric, then AGY minus y, that may not be 0. If y is in the column space, then it is 0, but it may not be 0. But if it is not a 0, then also this norm is least among the such AX minus y. So AX not equal to y. It can't be x equal to y because there is no such solution. But this is take any x. Now AX not equal to y. So there is a thing AX minus y norm. That norm is positive. Obviously, the right hand side is positive. Left hand side is also positive because there is no solution. But this is a list among all such x. Just take the special x, that gy, and for that value of g, that special g, if you take that special g and take x as a gy, then it is not a solution, but this distance is least. And we'll prove in the next video this. We'll show that in the next video that if we assume that AG transpose is AG, then this is hold, and this, if this hold, that least square, this is a least square, actually least square you need in the statistics for least square estimator. And this, for if it's a least square thing, then this AG transpose is equal to AG for the special G, and that G is called the least square G inverse. We'll prove it in the next video. And next we assume that all the three things, reflexive, and this reflexive, the norm is that rank of A equal to rank of G, and this all these nice properties hold. And it's special, if it is a solution, then the solution is the minimum norm. This is not a solution, this is a list among the all such things. And remember, if it is a solution, then both sides is 0. If y is a solution, then both sides is 0. So if it is not solution, then no. If it is solution, then the left side is 0. Right hand side may or may not be 0. Right. If you take the x as a solution, then right hand side is 0. Left hand side is gay is a solution. So left hand side is 0. The right hand side may or may not be 0. If you take x as a solution, there is 0. If you not take x as not a solution, there is not 0. But if no solution does not exist, then what happens? Then gy is not a solution. So both sides is positive, but still that left hand side is less than or equal, cannot be greater than that. We'll prove in the next video, and we'll assume that all three conditions hold, and then it is called Moore-Penrose G inverse. Then that means it is AG, GA both are symmetric, and AGA equal to A, and GA equal to GAG equal to G. And in that case, there is a special thing. One thing extra property is that this type of G inverse, all such three properties, extra property. So 4 condition actually hold. That is always exist. We prove in the next video that exists, and this is unique. But this least square and this other thing, the minimum norm and this least flexible, they may not be unique, but this is unique. So up to this, in next video, proof rest of the G inverse part.